correctly. Hello, I'm David. I'm the coordinator of the Maths Learning Centre at the Uni of Adelaide, and this is a quick, well, maybe not that quick, but it's a video about partial fractions for integration. Okay. Partial fractions is a method for rewriting rational functions. And so it's not really a technique for integration, it just happens to be useful for integration. But it's specifically an algebra thing, and it's designed for rewriting rational functions. And when I say rational function, I mean something that has a polynomial on the top and a polynomial on the bottom. And when I say polynomial, I mean anything from 1 plus x, 1 plus 3x plus 5x squared, anything that involves constants or powers of x added and multiplied by constants. And it's actually technically only a method for writing proper rational functions, by which I mean that the degree of the numerator is less than the degree of the denominator. So that's what proper means. In the same way as a proper fraction with numbers has the numerator smaller than the denominator, a proper rational function has the degree of the numerator less than the degree of the denominator. And when I say degree, I mean the highest power of x. Okay, so here's my example I'm going to use to make sense of this process. Example. Okay, so I'm just going to read it out. I have a fraction, and on the top is x cubed minus 5x squared plus 7, and on the bottom is x times x plus 1 in brackets, times x minus 3 in brackets squared, times x squared plus 25 in brackets. The process of the idea of partial fractions works when your denominator has been factorized first. That's the really important thing to know. So I'll probably add that just above here. Technically, it doesn't need to be factorized, but the process requires you to do that to be able to decide what to do. So I'm going to look at this is a rational function. The top is a polynomial and the bottom is a polynomial. The bottom, if I expand it out, will have degree x times x, and then an x squared. So I'm up to 1, 2, 3, 4, 5, 6, degree 6. And the top has degree 3, and that's less. Degree of the top is 3. And the degree of the bottom is 6. And so the degree of the top is less than the degree of the bottom, so it's a proper rational function. So the partial fractions will work for this. Okay. The point of partial fractions is to split your polynomial into several different fractions. Not polynomial, rational function into several different fractions. And I already can see a way of splitting it into several different fractions. So this fraction here, it's got x cubed on x times x plus 1 times x minus 3 squared times x squared plus 25. And it's got minus 5x squared on x times x plus 1 x minus 3 squared x squared plus 25, and it's got plus 7 over x times x plus 1 times x minus 3 squared times x squared plus 25. It's already possible to split it into 3 pieces just by separating this numerator into different bits. Lovely. That's great. But this is not going to help me if I want to use this for integration because I don't know how to integrate any of these things. I also know that if I changed this top, I would need possibly a different number of fractions. Okay, so I'm just going to change this a little bit and change it to plus minus 5 times this fraction plus 7 times this fraction. These three fractions, these three rational functions, if I change the numbers that went with them, would be capable of producing anything that had an x cubed and an x squared and a plain number on the top. So if I change this number up here, put a number in front of this and put a 4, then there'd be a 4 here. If I change this number here and put a 15, there'd be a 15 here. So I could choose to make from these lots of different rational functions. These functions here can produce lots of different ones. So what I'm going to do when I do partial fractions is I'm going to attempt to make all the possible proper rational functions that have this denominator. So if I think of all the proper rational functions that have that denominator, they're going to look like this. It's actually going to be a 5, isn't it? These are all, every possible proper rational function that has this denominator is covered by this expression. If I choose different numbers for A, B, C, D, E, F, then I will get, if I choose all the possible numbers, then I will get all the possible rational functions. So this is all. Okay, so this one I was capable of making out of 3 pieces. But if I want to think about what's possible for all the rational functions, many of them are going to need 5 pieces. And I'm just going to be really explicit and write them all out. These 5 pieces. A, lots of x to the 5 on x plus 1, x minus 3 squared. Plus B, lots of this. Plus C, lots of this. I'm just going to put a squiggle there to represent this, if that's okay, because I can't be bothered writing it out again. Plus D, lots of this. Oh, that's a cubed. D, lots of this. Plus E, lots of this. Plus F, lots of this. These are 5 separate functions, and when I combine them with multiplying them by constants and adding them together, I'm capable of producing all the proper rational functions that have this denominator. Okay, now, some people watching this may think that's a bit stupid, David, of course, right? But this is really important, that I know that these 5 functions are all different. I can't make any of them out of the other ones. And I create all these functions by doing a linear combination of them, by adding them together and multiplying them by scalars. So what I would like to do when I'm doing my partial fractions is choose a different collection of functions to go in these spots. Because at the moment, I don't know how to integrate any of these functions. And so what I'd like to do is, instead of writing this function back here as a combination of these 3, which I don't know how to integrate, I'd like to write it as a combination of functions that I do know how to integrate. So I need to choose a different collection of functions that will be able to produce anything with any proper rational function with this denominator. That's the goal, a different set. And because I know that it takes 5 functions to do this job of producing all of these things, I'm going to need 5 functions to do it. But what I'd like to choose is a different 5 functions. So I know, therefore, it takes six functions, A, B, C, D, E, F, sorry, 6 functions. It takes 6 functions to do this job. So therefore, to produce all rational functions with this denominator via linear combinations. I want to choose a different set of 6. That's the goal. Right. If you have studied linear algebra, then this action of doing linear combinations and producing all the answers is called spanning. And these things would be called a basis. We don't have to go into that, but it is exactly that. The problem is that in linear algebra, there are ways of finding a basis using matrix stuff. And here in calculus, it's going to be a bit trickier to find one. I'm just going to have to guess and try and find the ones I want. The theory of partial fractions says that there's a good choice for what they would be. But the theory of partial fractions is based on the fact that if I want all the rational functions with this denominator, then I'm going to need 6 other functions if I want to create it out of linear combinations this way. How are people feeling? Okay. Right. So the question is, which 6 am I going to pick? I know there are 6, but what I want is I want to pick 6 that I know how to integrate. Right. Okay. So let's just have a look at this function here. So point I want to make as well is if I want to integrate this function, I'm going to attempt to solve the problem for all the questions that could possibly be so that I can solve it for this one. So I know that every possible proper rational function with this denominator can be produced from 6 other ones. So I need to choose 6 of them. Okay. So here we go. I know that the function 1 over x is one of these. Because if I multiply the denominator by x plus 1, x minus 3 squared, x squared plus 25, and multiply the numerator by x plus 1, x minus 3 squared, x squared plus 25, then this is a proper rational function because the numerator's only got 1, 2, 3, 4, 5 on the top. Denominator's got 6, so that's good. And it has the correct denominator. So this is one of these functions. I don't know what the correct A, B, C, D, E, F from this expression are, but I would know if I expanded it out. So this is one of these functions. And I do know how to integrate 1 over x. So lovely. So maybe a good strategy would be to pick the pieces of the denominator and use them as new denominators to make new functions. So 1 over x plus 1, if I multiplied that by an x and an x minus 3 squared and an x squared plus 25, there's my x plus 1, and these are the missing pieces from the denominator. Then that is definitely true that this thing is one of these functions. And it's a different function from that one. So that'll work. Let's try another one. What about 1 over x minus 3 squared? That one. The missing pieces are x minus 1 and x squared plus 25. And so yes, this really is one of these functions which has that denominator. Cool, and I do know how to integrate this because if it was 1 over x, it would be x to the minus 2. And I integrate that to put the exponent up by 1 and divide by the new exponent. And the fact that it's an x minus 3, which is just a constant, like a linear function in x, means I can just divide by the derivative of that bit along the way. So I do know how to integrate this. Actually, look. I don't need actually the whole of x minus 3 squared, because just x minus 3 is a piece of this as well. And the missing pieces from just the x minus 3 is the x minus 1 of these x minus 3s, and x squared plus 25. So that'll work as well. And this is a different function to that. So I have 4 so far, I need 6. So the other piece of the denominator is this x squared plus 25. I'm doing this explicitly just to make sure that we're all absolutely clear that what's going on here. The missing piece of the denominator is this bit. So yes, this really is one of these functions, so it's good. And then I now have 5 different functions. If I want to produce all the possible functions, I'm going to need 6. And I've run out of pieces of the denominator. Now I could have x minus 1, but I don't know how to integrate that. I have to also know how to integrate this, to be fair. But trust me, it is possible. And I'll talk about that in a second. Will I talk about it now? I'm going to talk about it now, actually. Just trust me, you can integrate this. If this number here was a 1, then this would integrate to become arctan of x. So I'm going to make it a 1 by doing this. I'm going to multiply and divide the bottom by 21. And then if this was going to be arctan, this would need to be a single thing squared. So I'm going to write that as x on 5 squared. Okay, now if I cover that up, this is 1 over thing squared plus 1, which would, if I integrated it, become arctan of that thing. And as long as the derivative of this thing is a constant, all I need to do to fix it is to divide by that constant, because that's a rule for how integration always works. I have it under the just do it rule, and it works every time. So just as an example, I want to show you, if I had an example where I had sine cos of 2x, that would integrate to become sine of 2x, but I would divide by that too. Because if I differentiate this, it'll be a half times cos of 2x times 2 because of the chain rule, and the half and the 2 would cancel each other out, and I get a cos of 2x. So just as an example, if I did the same trick, e to the x on 5, when I integrate, I know that e to the x is the same as it was before, but I will have to divide by the constant that's multiplied by the x, which is a 5th. So for this function, I know that when I integrate this, the 1 on 25 will still be there because it's a constant multiplied on. This will become arctan of x on 5, but I will have to divide by that 5th. And so that will become 25 times a 5th is 5. Those who are extremely experienced with integrating rational functions are capable of remembering that this produces this answer. So 1 over x squared plus a squared will produce 1 over a arctan x over a. I am not that good. Don't do this often enough. Okay, so I have now convinced you that it really is possible to integrate this. But we only have 5 pieces, and I need 6. I'm allowed to do any functions I want. Any 6 functions will do, because of the way that the theory of linear algebra works. Any 6 functions will do, as long as they're all different, and I can't make any of them out of each other by just adding and subtracting stuff. And over here, These functions are different only because their numerators are different. So with these ones, I knew these were different because their denominators were different. What if, to make my sixth one, because I've run out of denominators, I change the numerator of this one? Because this is still one of these functions. The missing piece of the denominator is this, so I'll multiply my current numerator by those things. And let's just check. 1, 2, 3, 4, 5, 6. Just a second. I don't put that bit in because that was actually already there. Okay. I already had the x squared plus 25, so I don't put that in at the top. 1, 2, 3, 4, 5. It's still smaller than the bottom, so it's good. It is one of these functions. And I do know how to integrate this because the top is nearly the derivative of the bottom. And so I would use substitution. I could go u equals x squared plus 25. Then du on dx would be 2x. And then du would be 2x dx, and I can see an x dx, and so that would be half of du. So it would be much nicer if this was a 2x. And it's still one of these functions. I can choose whatever I want here, and it'll still be okay because there'll be 6 different functions. So if that's a 2x, then this becomes, the 2x dx becomes 1 lot of du. This becomes a u. And I get ln of the absolute value of u plus c, which is ln of x squared plus 25 plus c. Cool. So what I've done is I've chosen a different set of 6 functions that together, and I know all my functions are different, none of them are multiples of each other. It's not possible to produce any of them by just doing multiples of the other ones and adding them together. So these are 6 independent functions that are all part of this collection of the functions I'm trying to produce, and therefore they will be able to produce all the answers. I have now figured out that it is possible to solve any problem that has this denominator now. Excellent, I've solved all the problems and therefore I can solve this problem. All I need to do, all in inverted commas, all I need to do is figure out what the correct multiples of these things are. So just to step back a bit, I would like my function, minus 5x squared. I know that my function is guaranteed to be writable as a combination of these 6. So it's going to be something times 1 over x plus something times 1 over x plus 1 plus something times 1 over x minus 3 squared plus something times 1 over x minus 3 plus something times 1 over x squared plus 25 plus something times 2x over x squared plus 25. And what I need to do now is, and I'm absolutely certain that all these functions can be written with that denominator, and they're all different, so it's going to work. And there's the correct number of them. There's 6, because I need 6, because the numerator has up to degree 5, which gives you 6 unknowns. Right. So all of that reasoning tells you how to do this process. You put all the pieces of the denominator. Anything that's got a squared, you're going to include 2 pieces for that. If it had a cubed, it would have 3 pieces. Anything that's irreducible that I can't factorize, it's going to produce 2 pieces. One with a constant and one with the derivative of the bottom on the top. Now, this is not what is generally presented in the lecture material for Maths 1A at Uni of Adelaide, but it is part of the Mobius question, so we're allowed to do it. I don't remember. The ones that go with partial fractions, which would be quite recent. Well, unless you're watching this earlier and not doing Maths 1A, but you know, but for you guys, quite recent, they would be there. Okay. So how would I actually go about figuring out what these are? I'm going to do that with a different example because this one's really complicated, if that's okay. I'm going to do a slightly simpler example of showing how to figure out what the letters actually, what numbers the letters are. This one I don't feel like doing, it's too big and I won't be able to fit it in the time I have. So just know that it's possible. And since it is possible, that means that when I integrate this, it'll be a times ln of x plus b times ln of x plus 1 absolute value plus c times, all right, that's at x to the minus 2. So the power will go up to x to the minus 1 and I'll have to divide by minus 1 and divide by the derivative of that, which is 1 anyway, so that's okay. Plus d times ln of x minus 3 plus e times, now I just did that derivative. It is 1/5 of arctan of x over 5. Plus f times, and I just did that derivative too, ln of x squared plus 25. Plus a constant, I've already used c, so I'll call it k. And whatever these numbers are, that's what the answer is going to be. So if you wanted to do one of these to convince someone that you knew how to do partial fractions and you didn't have time to figure out what these things were, you could still write this answer down to prove that you knew what the integral was going to be like at the end, and you would get a mark for that in your exam. Not that I believe in exams, but if you're going to have to do them, you want to get as many marks as you can. Okay, so let me do a different example. And I had several of them written down on my notes here. I seem to have lost one of them. Very carefully worked one out. Okay. I'm very much hoping that my calculations are correct here. Here is an example. It looks really awful. So I have 22x cubed minus 23x squared plus 150x plus 510, all divided by x to the power of 4 plus 10x cubed plus 34x squared. Now the numerator is less, has a bigger degree than the denominator. Sorry, other way around. The numerator has a smaller degree than the denominator, so this is a proper rational function. So the process is going to work. And I'm not going to be able to do what I want to do unless I factorize the denominator. Do you know what? I'm not even going to write out what it's equal to. I'm just going to say the denominator is this. So they've all got an x squared in them, so I'll factorize that out. And then I would need to attempt to factorize this. Okay. So I might not quite complete the square, but just think about it. If I divide that 10 by 2, it would be a 5. And a 5 squared would be 25. And so, and this is more than 25, so it's not going to factorize. I'm just going to do that properly. That's me completing the square. This divided by 2 and then squared is 25. And when I factorize this, it's going to be x plus 5 squared. And 34 minus 25 is 9. This is not going to factorize, because for this to be equal to 0, this would have to be negative, and it's a squared, so it's not going to work. How do we feel about that? So if when you complete the square, you've got a plus here, it's not going to factorize. Okay, that's sad. It's not going to factorize that, sadly. So yeah, okay. All right, so the pieces I'm going to use are, actually, just to make it easier, I'm going to call this function f of x. So my f of x is going to be made out of pieces. I'm going to need 4 pieces because there's a degree 4 on the bottom, and also there's like, when I do the biggest powers I can, as there's 1, 2, 3, 4 pieces there. So I'm going to need to make it also out of 4 pieces. So one of my pieces is a 1 over x squared. And the next piece would be a 1 over x. And then I guess I'm going to do a 1 over x squared plus 10x plus 34. And they're all the bits of the denominator I've already got, but I've only got 3 pieces and I need 4. And so what I'll do is I'll change the numerator of this one. And the thing I'm going to put on the top is not an x, because I can put whatever I want on the top as long as it doesn't have 2 big powers. So I'm going to choose 2x plus 10 because that's the derivative of the denominator. So I'm going to have some number of this and some number of this and some number of this and some number of this. I do know how to actually integrate this, because if I do complete the square like this, then it looks quite like one of these, but with an x plus 5 instead of an x. And so what will happen is that when I integrate it, there'll be like an x plus 5 here. So I do actually know what to do with that. But what I'm going to do is hope that this one comes out to 0. Because if it does, then I won't have to do it. But if it doesn't come out to 0, then I'll have to deal with it. Okay. So now we're going to figure out what these letters actually are. Okay. Right. So the way to figure out what this, well, one way to figure out what these letters are is to put these all over a common denominator and write it as one big fraction that has this denominator. Well, technically this one. And then compare the tops, because if it is the same function, the numerators have to be the same as well. That's the classic way of doing it. So that's what I'm going to do. So I know that this is the same as a times x squared, and the missing piece from the x squared is an x squared plus, you know, no, I will do it. And so this will have an x squared plus 10x plus 34 on the top. That's what this one here became. And plus a b, and it was a 1 over x, so I need an extra x to make an x squared, and I need the x squared plus 10x plus 34. And c, I've already got an x squared plus 10x plus 34, so I'm going to need to multiply it by x squared. And d, I've already got an x squared plus 10x plus 34. So I'll have to multiply, and on the top there's a 2x plus 10 already. I'm going to need to multiply that by an x squared. And now I have one, all these have the same denominator, so I can add them together to make one big fraction. I don't feel like writing that denominator down, but no, I'll be fine, I'll be fine. So let's see if I can skip some of the working. Do I really want to do that? No, I won't. I'll skip the working in the next example. Right, that bit I can skip. Okay, so this thing is equal to we've got ax squared and 10ax and 34a here. And here we have b, and this multiplied through will give me an x cubed, a 10x squared, and a 34x. So I've got bx cubed plus 10bx squared plus 34bx. And this one will give me cx squared, and this one will give me, oops, sorry. And this one will give me d x squared times 2x would be times 2x cubed, and this one will give me d times 10x squared. And all of that over x squared plus 10x plus 34. And this is supposed to be equal to this. So since these two functions are supposed to be equal and the denominators match, then the numerators must match as well. And the only way for two polynomials to be equal is for their coefficients to be equal. So what I will do is compare the coefficients of the numerator. And in fact, in my working, I will write down the words, compare coefficients of numerator, just so whoever's reading this knows what I'm doing. All right, here we go. In this version, the x cubed, there's one here and there's one here. So the coefficient of x cubed in this version, it's b plus 2d, but back in the original function, it was 2. And the coefficient of x squared, now let's see, x squared, there's one here, there's one here, there's one here, there's one here. Oh, that's horrible, but there we go. We have a plus 10b plus c plus 10d, and all of that is supposed to be minus 23. And then I'll look at the coefficient of x, those ones. All right, 10a plus 34b. And that's supposed to come out to 150 according to my original function. And then the constant term, over here, it's 34a. And that's supposed to come out to 510. Right. So I now have 4 equations and 4 unknowns. If I had a computer handy to help me do the row operations, I could put in a great big matrix and row reduce, and that would give me the answer. Or I could try and sub things in along the way, because this will tell me what A is. I'm going to number my equations. 1, 2, 3, 4. So from 1, A is 510 divided by 34. For which I'll need a calculator because I can't be bothered trying to do that myself. It's 15. Awesome. It's almost like I set it up this way. And then if I sub that A into this one, it'll tell me what B is. Sub into number 3. No, that's number 4, sorry. Sub into number 3. 10 times 15 plus 34b is 150. And so 34b, well, 10 times 15 is 150 will be 0, so b is 0. Oh, how convenient. It's not the one I was expecting to be 0. I hope I've labeled my letters the way I expected it to be. Okay. And I can sub that back into number 1. And so b plus 2d is 2, but b is 0, so 2d is 2, so d is 1. And then I can sub everything into number 2 to figure out what c is. So a plus 10b plus c plus 10d equals minus 23. And so I've got a is 15, b is 0, C we don't know, and D is 1. And so C would be minus 23 plus 15 plus 10, which is minus 23 plus 25, which is 2. And so that means I can now actually do my integral. Well, theoretically. Okay. I think I labeled everything right. I'm just going to trust it. So that means that my original function, which was called f of x, so I don't have to write it again, which is nice, is actually this. It's a, which was 15, times 1 over x. There's my original working, a times 1 over x squared, plus b times 1 over x, plus c times 1 over x squared plus 10x plus 34, plus d, which was 1, wasn't it? Yep. Times 2x plus 10 over x squared plus 10x plus 34. Yeah, I feel like I've done something wrong because it doesn't match my original working, but whatever. Dx. And now I need to know how to integrate those things. So I've got 15 times 1 over x squared. That I know how to integrate. I'll be okay. I'll write that as an x to minus 2 and I'll be fine. We don't have any of those, so that's fine. 2 lots of, now I have to rewrite this as, in order to integrate it. This one will work out to 15 power up by 1, x minus 1 divided by new power, plus 2 lots of, I'm going to shortcut this. I know that if it was just an x, it would be 1/3 of arctan x on 3 by doing the same process I did before. But it's not an x, it's an x plus 5, so that's fine. You would actually have to show the working for that if you're in an exam. Plus, and if I do the same thing, this is the derivative of the bottom, so it's going to be 1 over u. And so it's going to be ln of x squared plus 10x plus 3. And I've technically already used c, so I'll call it k. How are we feeling? It would have been much nicer if this one had been a 0, but it didn't work out that way. Yeah, this was bizarre because it's not, I'm bamboozled because it doesn't match my original problem. So I've probably done something horribly wrong, but everything's turned out to be whole numbers. So I'm going to just believe it for today. I feel uncomfortable, but it's okay. You need one more example. So how are you feeling about that one? All right. So my other example is 4x plus 16 over x to the 4 minus 16. Right, so let me just check. This is a rational function that has the numerator degree less than the denominator degree, so it's going to work. And I'm going to have to factorize the denominator. Now, factorizing quartics is not always fun, but I do notice that both of these are squares. This is x squared squared minus 4 squared. And so this will be x squared minus 4 and x squared plus 4. Now, this one, this can't be 0 because x squared is always positive, so that one can't be factorized. This one, well, it's also a difference of 2 squares, and so this will be x plus 2, x minus 2. And that's as far as my factorization can go. So I might even call this f of x. just so I don't have to rewrite it all the time. So f of x is now equal to, is going to be equal to things that are built out of this denominator. So a 1 over x plus 2, some multiple of that, and a 1 over x minus 2, some multiple of that, and something, and 1 over x squared plus 4, some multiple of that, and if I put the derivative of the bottom on the top, it'll work very neatly for me. So these three are the pieces of the denominator, and I ran out. I need 4 because there's a degree 4 here, because I know that even though this only has 2 pieces, if I want to make it out of other bits than the ones that it's currently made of, I might need 4 of them. And so I need a 4th one, and so I will change the numerator of this one that has the squared. Okay, and let's pop that over a common denominator. This is going to be a lots of x plus 2, x minus 2. Okay, just a second. This is where I'll skip some of the work. So I'll put over a common of x plus 2, x minus 2, x squared plus 4. Okay, I'm just telling the reader what I'm doing. Okay, and so the numerator will be, so this one I'll have to multiply the top and bottom by this x minus 2, x squared plus 4, because that's what's missing. And so it will be a lots of x minus 2, x squared plus 4. This one I'll have to multiply by these two because that's what's missing. So it will be b lots of x plus 2, x squared plus 4. This one, this is what's missing. So it will be c lots of x plus 2, x minus 2. And this one, this is also what's missing. So it will be d times 2x times x plus 2, x minus 2. That's my numerator. And if I want to match that up with the original numerator, I'm going to need to figure out what the coefficient of everything is, which means I'm going to have to expand all those brackets. Oh, damn it. So I've got an x cubed, I've got a 4x, I've got a minus 2x squared, I've got a minus 8. And here I've got an x cubed, I've got a 4x, I've got a plus 2x squared, and I've got a plus 8. And my c, I've got an x squared. Oh, that's x squared minus 4. Okay, I did that one already. And this one, I've got a d times 2x times x squared minus 4. So that would be 2x cubed minus 8x. And this is supposed to be equal to this. So I'll compare the coefficients. So the coefficient of x cubed, now there's an x cubed here and here and here. So I have a plus b plus 2d, and that's supposed to be 0 because there aren't any x cubed in this one. And the coefficient of x squared, all right, so there's one here, and there's one here, and there's one here. So that will be minus 2a plus 2b plus c, and that's 0. And the coefficient of x, there's one here, and one here, and one here. That will be 4a plus 4b minus 8d, and that's 0. And the constant term is here, is minus 8a plus 8b minus 4c equals 0. And I do not like my hope of solving this without a matrix, because there's 3 unknowns in every one of these. So if I were going to solve this, I would go, well, this is how many a's, this is how many b's, this is how many c's, and this is how many d's. 1a, 1b, no c's and 2 d's is 0. Minus 2 a's and 2 b's and 1 c and no d's is 0. 4 a's and 4 b's and minus 8 d's and sorry, no C's, and minus 8D's is zero. This one, crap, damn it, David, stop. They're not all 0. Coefficient of X is 4, and the constant term is 16. Damn it. That's just got carried away there. Yeah, coefficient of X is 4. And so this will be minus 8A and 8B and minus 4C. So that is 16. And if I row reduce that matrix, it will tell me what A, B, C, and D are. But I would need to actually get a machine to do that because, well, I mean, it's theoretically possible by hand, but that's what machines are for. Let's see what my machine does. Actually, just a second. Oh, look, if I had them both on the same screen, it would be good. That's 4 by 5, was it? Oh. And so I have 1, 1, 0, 2 is 0. And I have minus 2, 2, 1, 0, 0. I have 4, 4, 0, minus 8, 4. And I have minus 8, 8 minus 4, 0 is 16. And then I'll do REF of A. And that tells me that A is minus 1/4. B is 3/4. C is minus 2. And D is minus 1/4. Yay. And therefore, the integral of my function is actually the integral of minus 1/4 of, where's my function? Just a second. Here it is. 1 over x plus 2. No, that's the wrong one. No, that's right. 1 over x plus 2 plus 3/4 of 1 over x minus 2 minus 2 of 1 over x squared plus 4 minus 1/4 of 2x over x squared plus 4. And so the integral will be minus 1/4 of ln of x plus 2 plus 3/4 of ln of x minus 2. Need the absolute value signs, by the way, that's important. Minus 2 of, now, how did it work? It was this, the square root of this. So 1/2 times arctan of x on 2 minus 1/4 of, now that was just ln of the bottom, plus constant. Yay! And that is partial fractions. I hope that was helpful. Sorry? I will not do any more for 1A, but I'll be in the Maths Learning Centre.